Let's discuss quantum numbers and electron configurations. In a previous video, we discussed the first two quantum numbers, that of the principal quantum number, the shell, which tells you the size of the subshell, also the energy associated with that electron, and then also the angular momentum quantum number. So this is your subshell, and remember we have the S, P, D, or F, and they get L, or angular quantum number assignments of 0, 1, 2, or 3. You could also go to G, which is 4, but we typically don't use those in our class. All right, so the S, is a sphere. It has one orbital and can therefore hold 2 electrons. The P is dumbbells. It has 3 orbitals, each orbital holding 2 electrons, therefore you get 6. The D is 4 flowers and then one that looks like a donut with a dumbbell in the middle. So there are 5 of those orbitals, and each orbital can hold 2 electrons, so total there are 10 electrons max in the D subshell. The F, all kinds of fun, crazy shapes. And then those are 7 orbitals for a total of 14 electrons possible in the F subshell. So these we've already looked at. If you don't remember them, go back and look at previous videos. The first quantum number we're going to look at today that is new is the magnetic quantum number. What this quantum number is going to tell you about is which specific orbital within the subshell the electron's located in. It can have a value from a negative L to positive L. What does that mean? Basically, it's just going to tell you which direction the orientation is in space. So with the sphere, if you rotate a sphere, you're not changing the orientation in space. So there's only one magnetic quantum number possible. If L is 0, you can go from negative 0 to positive 0. What's in the middle of that range? Oh, only 0. Okay, there is no positive or negative 0. It's just 0, which means the magnetic quantum number for a spherical orbital is just going to be 0 because the S subshell has an L of 0, and therefore the M sub L, the magnetic quantum number, is also 0. But if we look at the P orbital has a L of 1. And so the magnetic quantum number can be anywhere from -1 to +1, so it could have 3 different orientations in space. And so we're just assigning that X orbital of a -1, so that's along the x-axis. The one around the y-axis is going to get an M sub L of 0, and then that along the z-axis is going to have a +1. And these are just assigned arbitrarily, okay? It's not like the electrons know, hey, I'm in this orbital, therefore I must have a quantum number of 1. These quantum numbers are just going to help us figure out what's happening with all the electrons around the atom and why. And so assigning these magnetic quantum numbers or just quantum numbers in general can be helpful, as we'll see in a minute. All right, so this is for the L of 1, which is the subshell of a P. What about the D subshell? So the D subshell has an L of 2, which means the M sub L can be anywhere from -2 to +2. So it can be -2, -1, 0, +1, or +2. And you can see those assignments right there. And then same thing for F. For F, you have an L of 3, so you can go anywhere from -3 to +3. And that is why we started out with S of 0 and then going to F being an L equal to 3. And so you can see these assignments here. So basically, you just know that they're all different, and every orbital has a different magnetic quantum number. If we look at this slide, this is kind of a summary of them all. If you look at the n=1 energy level, so the principal quantum number of 1, you can maximally have an L of 0. And so this is why there is no P subshell within the principal quantum number of 1. You can only have L equal to n-1. So if your n is 1, your L is 0, which means you can only have a 1s. You cannot have a 1p. And so then your M sub L is the same. You can only then have a 0. And so that's why there's only one orbital within the energy level of 1. Whereas if you look at n equal to 2, you can have up to n-1, which means I could have a 0L or a 1L. Therefore, I can have a 2s and a 2p. Both are possible. So then within the S, you have an M sub L of 0, and within the P, you have -1, 0, and +1. So a total of 4 orbitals possible within the principal quantum number of 2, and so on and so forth. And so that's kind of how these work and how they all add together. But the main takeaway is by figuring out these rules for quantum numbers is that we know our energy level of 1 only has an S. Our energy level of 2 has an S and a P. Our energy level of 3 has an S, a P, and a D. And then for F, S, P, D, and F. But you do not have a 3F. That orbital does not exist. It cannot based on the rules for quantum numbers. All right, let's look at the final quantum number, that of spin, the spin quantum number. One important principle states, Paulie's exclusion principle says, in a given atom, no two electrons can have the same set of 4 quantum numbers. Electrons cannot exist in the same space. You could see how that would be very, very bad. And so even if you have any of these orbitals that we see before, so let's say we have an F orbital, you can't have 2 electrons that are taking up the exact same space. But we know that 2 electrons can reside in any orbital. So if they're both in the same orbital, how do we differentiate the space that one electron is taking up as compared to the other? And we differentiate them based on spin. We arbitrarily say one is going up and one is going down, or one's going clockwise and one's going counterclockwise. And so the spin quantum number is going to describe the spin of the electron, where we assign an imps of S of positive 1/2 if it's got an upward spin and negative 1/2 if it's got a downward spin. And this does come into handy and really is very helpful and played out when you get to organic chemistry. But for right now, we're just going to assign and talk more about it as in generalities of up and down, and we're not going to worry about the ramifications and how this is very useful for imaging and figuring out what the what chemical substances are. But this is very helpful for us in the future. All right, so upward spin, positive 1/2. Downward spin, negative 1/2. So kind of in summary, look at this diagram. This is an energy diagram where energy is lowest in 1s. And if you look and you just kind of look up, going from 1s to 2s to 3s to 4s to 5s, remember, as you increase your principal quantum number, you're increasing the energy. That's why 1s is at the bottom of the energy diagram and 5s is all the way at the top. Then look within the 2. See how there's 2s and there's 2p? P's have more energy than s's. And so P are greater, they're higher up than the 2s. And then the same thing for 3s. Your 3D is greater than your 3P, which is greater than your 3s. So that's something that's always true. Your S is lower energy than your P, which is lower energy than your D. And if you had an F for the 4, so 4s, 4P, 4D, and then 4F, your 4F would be even higher than the 4D. But notice something here. Look at 3D and look at 4s. Which one has lower energy? The 4s does. So since 4s has lower energy than the 3D, electrons might actually want to go into the 4s before 3D. Whoa, 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 what did I say there? All right, this is a very important principle. Your electrons are lazy. They're lazy. If they're asked to take the elevator or the stairs, they're going to take the elevator. They want to exist in the lowest energy conformation possible. This is what makes bonding so helpful and so easy to predict. So your electrons, if they have a choice as to whether they're going to go into 4s or 3D, it's going to take a lot less effort to make it to the 4th floor than it is to make it to the 3rd floor level D. Okay, so they're going to land, if you will, into 4s. So this energy diagram allows us to predict where electrons are going to reside in. They're going to start out residing in 1s, and then they're going to go to 2s, then they're going to go to 2p, then they're going to go to 3s, then 3p, 4s, 3d, 4p, 5s, 4d. So you see kind of how we're kind of going through energy, and we're saying, all right, start with the lowest and make it all the way to the top. And so why it does this is, let's say we have 3 electrons. Your first electron is going to make it into the 1s. The second electron is going to go into 1s too, because every one of these orbitals, which are designated by a line, every one of them is going to correlate to 2 electrons. So your first 2 electrons get to reside in 1s. Your third electron is going to come along and say, I want to go in 1s too, but it's filled. It's occupied. So it has to increase and go to a higher energy level, that of 2s. If you have 5 electrons, your first 2 are going to fill 1s, your second 2 are going to fill 2s, and that 5th electron, where's it going to go? Is it going to go all the way up to 3s? No, it's going to hop over to the 2p orbitals. So the idea here is Aufbau's principle, which is going to say electrons are going to enter the lowest energy level first, and this is pretty important. And so I always draw, when I was in Gen Chem, I came and I wrote this at the top of my exam as soon as I walked in the classroom, because this reminded me of what order it is that stuff will enter. So follow the red arrows and then use the yellow arrows to connect each tail, each little arrowhead to each tail. So you go 1s, 2s, go on up to 2p, then 3s, then 3p, 4s, 3d, 4p, 5s, then back up to 4d, and then you'll just follow it in this order. But you have to remember, there is no 1p, there is no 2d, there is no 3f. Those just don't exist. Okay, and that's because of all the principal quantum numbers. So this this diagram is going to show us where do we place electrons and why. So for instance, if we take nitrogen and we look at nitrogen on your periodic table, it has a atomic number of 7, which if you remember back at the very beginning, if it has an atomic number of 7, that means it has 7 protons, and if it is neutral, it also has 7 electrons. So I need to put these electrons in here. So the first electron gets to go in 1s. The second also gets to go to 1s. The third has to jump to 2s. The fourth to 2s. And then there are still 3 electrons remaining. So the Hund's rule now is another important rule. There's like multiple Aufbau's, Paulie's, exclusion principle, and Hund's rule. These things matter and help us figure out how do we place electrons into these different orbitals. So we have 3 electrons left. Where do we do with them? We could put 2 in the first box and then 1 in the second box. But Hund's rule states electrons want to singly occupy every orbital before becoming doubly occupied. That means if you're given the choice between having a room by yourself and having a room with a roommate, and let's say the roommate's annoying, we're not assuming it's an attractive person that you want to room with, okay? But if it's just a random roommate that you don't really want to room with, think of that like Hund's rule. Hund's rule says if a single occupied room and a doubly occupied room cost the same amount, you're probably going to choose the single. And so that's what electrons do. They each take up their own space and spread out before being forced to occupy with another electron. All right, and then also notice they're all up. So the rule is the first electron has a spin up, the next electron that joins it in the orbital is spin down. Okay, so that's our Hund's rule here. This is how we occupy them. So when we're thinking about orbital configurations or orbital diagrams, you'll hear it called both things. What we're saying is that these boxes represent orbitals. Every S has 1 orbital, every P has 3, every D has 5, and every F has 7. And so then you place the electrons in these orbitals in the order that's based on energy, and then you're able to predict how electrons reside in these different orbitals. And then once we do this, we can then look at any single electron and figure out what its quantum number is. You'll also see me more often doing line diagrams for the orbitals, where every line stands for a different orbital. I do this because it's quicker, but if you like the boxes, feel free to do the boxes. So I will do lines, but boxes are also very common. So once again, though, these are called orbital configurations, and you'll just fill them in with little up or down arrows, just like you see here for nitrogen. So these are called orbital configurations or orbital diagrams.